Um, so just to summarize, what apart from introducing the general problems associated with high TC superconductivity in the cuprates, I reviewed a standard and old theory of the formation of superconductivity from spin fluctuations. So in that theory, you start from a Fermi liquid, and then you include antiferromagnetic spin fluctuations. And in fact, for the geometry of the square lattice, where the antiferromagnetism is pi, you do indeed get dx squared minus y squared superconductivity, which was later confirmed experimentally. I think I made a incorrect remark yesterday in response to a question. It is circular from its surface. It's dx squared minus y squared rather than dx, because the antiferromagnetism is at pi. It's that picks a direction, and that's enough to make the superconductivity have the x squared minus y squared. All right, so
Also mode, rotation.
I mean, there's no broken symmetry. It's not exactly circular, of course. Yeah, it's just some have that system pick pick out dx squared minus y squared. Put it up here so I get. So I want to first of all take a point of view that already also goes back where you start. We have antiferromagnet, but let's say from has quantum fluctuations, and you get a spin liquid state. So we want to first of all understand spin liquid states. So in the case there. So we can now talk about more authoritative math. And then I will apply a theory that, or some variation of a theory in a modern of what happens when you the spin liquid allow for either by dope in a Hubbard model. And it was already known in the early days that for certain spin liquids, several papers showing that. So that sounds very exciting, but as I'll show you today, well, I was also recognized already, there's some problems with this. We just apply it the way it was applied, and the way I'll apply it today, it leads to some issues with the nature of the superconductivity, and the numbers just don't work out to compare with what you observe in the experiments. So for that reason, this particular approach seems to have faded away. Well, after quite a bit of work. But in my next lecture, I will show how to fix this problem. And the key is really understanding the pseudo-gap metal phase better. And once you put that physics, in fact, this also works. So you end up getting the same superconducting state. So you can think of this, which I'll introduce as ECS root to ECS superconductor. This is, of course, a small variation of the ECS root, just replace the phonons, spin fluctuations. Okay. So, but the is not fundamentally different ECS state. It's just the way you get there, the mechanism is good. So that's kind of what I'm going to talk about today in a modern, much more general language. All right, so so I want to just get right to the current understanding of what a square lattice spin liquid looks like. So we start from the nearest neighbor model, which of course has long linear order, but now you put in some frustration. You put in the second neighbor, or you put in a certain force spin coupling that Sandvik puts in. Then you ask, what is the first spin liquid you encounter after you lose the nail state? Now there's very little doubt of what the answer is. And now we want to understand that spin liquid better. And it's taken quite a while to understand that spin liquid. where we reached today. So I'm going to summarize that now. So what we did yesterday was begin with the bosonic parton method. So you write the spin operator in terms of bosons with a constraint, one on every side. And then because of this constraint, there's immediately a gauge invariance that's present in the Hamiltonian for the bosons. For a while, you just ignore that, and then you put the spin operator here, and you just do some Hartree-Fock mean field theory, Hartree-Fock BCS mean field theory on the partons. And after some numerical work, you find that the best solution is really quite simple. It looks something like this. It has a Hartree-Fock mean field value of this field Q, which you can think of. So there's a condensate of Q, and what is this operator? Well, this operator is just an operator that creates a singlet bond. Now, you can't just create a singlet bond out of nothing. What you can do in the physical system is resonate between different singlet bond configurations. So, so this operator acting on the vacuum state of the partons this is just nothing but what I was drawing in pictures as a singlet bond between two sides. Now, in the real system, what happens, of course, is that you do have lots of singlet bonds, but they don't just disappear into nothing. They resonate between, say, this configuration and this configuration. So you're never really, so here, this state is an unphysical state, and it doesn't have the right number of partons on it. So you create it and you get a physical state. Here, every state is physical. There's exactly one parton on every side, but the singlet bonds have resonated. So what's happening in mean field theory, roughly speaking, is that you've replaced in the state of singlet bond. You have a singlet here. Simple picture is 1/2. So there's a condensate here, and just taking a mean field condensate. Now you have to put the constraint back in, the physical state, and that's going to be done by the fluctuations. Okay, so you get this mean field theory, and then we think of fluctuations about the mean field. So here, the most important thing, again, is gauge invariance. And as I said yesterday, there's a certain Goldstone-like mode you can imagine in the gauge fluctuations by imagining that you do a gauge transformation, which is staggered, which has one sign on one sublattice and the other sign on the other sublattice. Then you don't change the condensate. Well, if it's uniform, and if it's varying, you're going to get some low energy fluctuations. So to figure out what the action of the fluctuations is, you just take your mean field Q. So this would be QR, I guess. And you focus on the phase of it. You write it in this way. All right. So now what you do, which I will not do on the, but it's in detail. Every step is stepped out in the notes. You insert this ansatz into the Hamiltonian. And then you just expand about this mean field solution. Take a low energy mean field and expand everything. And when the dust settles, you get something very cool. You get that field theory at the top there. So that's sometimes called the CP1 field theory. That's a Lagrangian in 2+1 dimension. And you can really see the full derivation of it in the notes with nothing swept under the rug. This A mu is the spatial components of A mu are related to this in some with some staggering. The time component of A mu is related to the fluctuation of the Lagrange multiplier. And the Z's are some linear combination of the Schwinger bosons, of these partons, the linear combination of B and B dagger on the two sublattices. Okay. And then you can imagine that, so this is just, first of all, the nice thing about this theory is that it's clearly gauge invariant. There's a gauge field, which will have the usual transformation of a U1 gauge field. These are bosons. It has a relativistic form. Now, sometimes you get the question, how can you have spin-and-a-half bosons in relativistic Widmer spin statistics theorem. It is, but this spin here is not Dirac spin. It's not an angular momentum. You can just think of it as some flavor index. It has nothing to do with Lorentz spin. So this is really the way to think about it. It's a field theory. If you want to talk to a particle physicist, you tell them it's a field theory of two complex scalars. In the alpha, they're scalars, they're not vectors. As far as particle physics are concerned, they're two complex scalars, alpha being the spin, the flavor index. And also you could imagine, doing a little bit of RG, and then by gauge invariance, you will get a Maxwell type term. The whole thing, as you near the transition where the Néel order is weak, some critical point R here. So there's a critical point when this mass changes sign, has a relativistic form. It's quite remarkable, but it's true. You can see the full derivation. Yeah. No, there's no Chern-Simons term here. Yeah.
So the Qij
Yeah.
is, I guess I'm confused a little bit about the gauge field.
Yeah.
It should be the bond variable on the doubled unit cell. But
Well,
here it appears like
you have to look at the notes. There's a little, this is the transformation of the Aij under gauge transformation. Is Aij going to Aij plus phi I plus phi j? So that, because of the B dagger. But if you take the staggered gauge, which is what you have to do, then it becomes gradient of phi. So that's what I did. Somewhat complicated here and the A there. And
ranging now over
nearest neighbors.
cell.
Well, I mean, I'm allowing them to have an arbitrary spatial variation. I just take the saddle point.
Double unit cell, they're staggered. It's
Approximately, yeah.
And then
So another way to say it is that I'm allowing IAG to be completely arbitrary in space. I'm focusing on the components of Aij that in the continuum limit, which are near pi. Yeah. It absolutely enters in everywhere. This doesn't work on the triangular or Kagame lattices. I mean, the simplest way it enters into the fact that this Qij is a bipartite structure. So I can define an A sublattice and the B sublattice. And what you notice from this here, that the Z has one charge, it's a B on a one sublattice and a B dagger on the other sublattice. So it has a positive charge on one sublattice, and then the bosons have a positive charge on the A sublattice and a negative charge on the B sublattice relative to this gauge field A mu. And that's ultimately related to the fact that if the bosons have opposite charges on the two sublattices, it doesn't change. It would work on ego. Yeah.
You mentioned these are two complex scalar, but at least what's written here has SU2 symmetry, right?
That's a flavor symmetry, right? Correct. It does have SU2 symmetry. That's simply the SU2 symmetry of this Hamiltonian is the global SU2 symmetry here.
So what's the meaning of we should not think of this as spinors, just to not angry high energy physicists?
No. I mean, they are spinners in the flavor space.
No,
they're
but they are spinners.
They are. I mean, they're not direct spinners. They're not. They're not spinners under Lorentz transformations. They're spinners under rotations in spin space. Now, if you have a fully physics theory, rotations in spin space are part of rotations in orbital space. They're coupled together. Okay, they're not coupled here. Now, if I had a spin-orbit interaction, then those issues may come up. Okay, but I don't.
I understand the Néel order. I want to know, how do I know that the other phase is a VBS phase?
Okay. All right, I'm coming to that. All right. I'm not going to explain it because, that would take the rest of It takes some time to understand that, and it's explained in some detail in my book. I am going to kind of derive that in a different way today. So that's why I'm not going to explain. All right. So, but that leads me perfectly to the next point. This is not the whole story. So this is what happens when you look at small fluctuations. So this is sort of analogous to, when you're doing something, you have some XY model and you're just looking at fluctuations of small amplitude and phase, and then you get spin waves and so on. You're getting a photon. But you can also look at large fluctuations. So for the XY model, that's a vortex. And Costas-Thales told us that vortices are the key to understanding the transition in the 2D XY model. Okay, so this theory, so imagine you're in a regime where R is very large. So you're deep in some spin liquid phase found by Horowitz and Auerbach. Then you can imagine just getting about Z, and your theory is just pure electrodynamics. Okay, so this part here, pure electrodynamics in 2+1 dimension, is the exact analog of the spin wave theory for the XY model. For the XY model, your theory is just grad theta squared. Okay, when you're at very low temperature in the XY model. So here, when you're large R, your low energy theory is just F mu nu squared. So this thing, if you quantize it, it gives you a photon, just one photon in 2+1 dimension. There's not two polarization, there's only one. But then has some relativistic dispersion. So you would say, here's a spin liquid, and there should be a photon excitation that you could measure if you were clever enough. But what Costas and Thales showed was that eventually, if you raise the temperature in the XY model, you had to worry about vortices. You had to worry about these topological defects, and they would proliferate in some transition. The similar question at the same time was asked by Polyakov for electrodynamics, pure electrodynamics in 2+1 dimension. And the answer is a little bit different. So in this case, there are also topological defects in electrodynamics, and they're simply Dirac monopole. So imagine a situation in three space dimensions. If you have a magnetic monopole, it has electric flux going on around in three directions. So here also, there are these monopoles that are allowed. And understanding the role of these monopoles in all these different spin liquids has been difficult. It's taken plus years to sort all of that out. But especially in a recent paper by Ashwin's group, many of the things are now. Anyway, so what did Polyakov show? So the Polyakov showed was that, again, these monopoles are always relevant. So they started proliferating. And in the language of particle physics, he would say that leads to confinement, that these d alpha particles should then confine. They're charged particles, they will confine because of the proliferation of monopoles. Okay, again, I won't go through, but it's a calculation quite similar in spirit to the Costas-Thales calculation, because Costas-Thales mapped the theory of vortices to a Coulomb gas dimensions. And amazingly, this maps to a theory of Coulomb gas in 3 dimensions. However, a Coulomb gas in 3 dimensions is quite different from a Coulomb gas in 2 dimensions. A Coulomb gas in 2 dimensions has 2 phases. It has the bound phase with vortices and anti-vortices bind, and there's the proliferated phase where vortices unbind and you get short range order. In 3 dimensions, it turns out there is no bound phase. And that's what Polyakov showed. I don't think he was aware of Costas-Thales' work. It was all happening around exactly the same time. So in fact, the monopoles are always unbound. No matter how small your E, no matter how large your stiffness, no matter how weak your electric coupling, they're always unbound. So this tells us here is that this theory, this is a dynamical effect. It's not a symmetry effect or something coming from some fancy topological argument. It's a dynamical effect. You actually need to know the Lagrangian, which tells you that, in fact, the spin liquid is unstable to confinement. All right. Okay, so you might conclude that and say, all right, so then this thing The confined is an end of story. But then you run into a problem. So then you find if this is confines and nothing else happens, then you have a gapped state with no broken symmetry for a spin-a-half antiferromagnet on the square lattice. And we know now by the Lipschutz-Mattis Hastings-Hoshikawa theorem, it's impossible. All right, so resolving that, well, how does this all get resolved? This is something Nick Reed and I showed a long time ago. These monopoles come with some Berry phases, and when you put those Berry phases in, you find that the Polyakov confinement leads to the valence bond solid. All right, so that's a quick summary of a subtle effect, but in the end, once you think in terms of what's allowed, it's pretty clear that this is the only thing that can happen. You can't get a trivial state. You have to break translational symmetry, and indeed, when you do the calculation, you find you do exactly this way. All right, and the nice thing is then, since then, a lot of numerical studies of this square lattice antimagnet, as I mentioned, and pretty much all of them see exactly this. All right, so that's great. So we've understood the square lattice antiferromagnet. Only trouble is, starting from this picture of spin liquid, this is my almost spin liquid, if you wish. And maybe there's a spin liquid at this critical point. I'll come back to that. So does this spin liquid have anything to do with the cuprates? So the simplest question you can ask is, does it give you superconductivity? So that's been a complicated thing. And the answer is, it's not at all clear how and what type of superconductivity. There's no natural connection between this and superconductivity. So we turn to another approach, which already in the early days, people understood spin liquid is almost a superconductor. But on the other hand, when you compare with numerics, it didn't seem to agree. But now we understand that, in fact, in the end, this is the punchline in a way, fermionic theory is a certain fermionic theory. It took a while to figure out which one. A certain fermionic theory is exactly dual to this one. So that's the one we should study. And that also gives you also superconductivity. So finally, everything's starting to hang together. Yes.
So am I correct in calling this the DQCP?
Yeah, that's what we would.
Is there a way we talked briefly with Senthil about how there's these complex critical points.
Oh, yeah.
Is there a way to see that from this picture, or that there's more information I need to add to the low energy theory?
I mean, from field theory, there is just a conjecture. There's no field theory calculation of complex critical point. Recently, there's been people studying, doing bootstrap on certain field theory, finding pretty good evidence for a pi-critical point. So anyway, all right, I'll come to that a bit later.
What's the relation between J and RC?
Not much. You can think of this roughly as J2 over J1. So, the value of J is nothing, it's just the energy scale. It's just in front of the Hamiltonian and can determine the ground state. Only ratios of couplings can determine couplings in the field theory. Yeah.
So this phase diagram, say that that's like the correct phase diagram for the J1, 2.
We know from numerics, yes.
So if you said that the fermionic picture should give us exactly the same picture, if you do everything exactly,
Yeah.
what's the point of?
Well, but you can't do everything exactly. So the question is, which approximate procedure in the fermionic?
But if you have some mean field answers,
We have more than one. We had hundreds. Yes, people have worked on a lot of them.
all going to be standards that gives you this thing, right?
Yes. So that fact was only understood a few years ago by this paper of Chong Wang et al. Well, I'm reviewing their work, but it's a few years from my time scale, maybe not your time scale. It's a very recent history as far as I'm concerned. But it's what I was telling you so far is ancient history. Yeah.
You say that that's the correct phase diagram from numerics, not for SU2.
For SU2, yes.
I get stripes at big J2.
That's much bigger J2. So yeah, so there's another phase here. You're right. But that is not described by this theory. There's another theory for it with ordering at pi0. You get analogous effects with those states too. But out here, yes, there's a state which is magnetically ordered, which is like this. And there's no way, this is a strong first order transition. It just jumps. So we're not worrying about this. You can do a theory of this that has its own VBS states. No one's really studied that carefully. But this state is sort of analogous to this, and there's another copy that applies here.
So just speaking about the numerical expression, there is a range of objections for which one thinks that there's a VBS there.
I think it's pretty well established. The arguments are all about exactly what's happening at this critical point.
But I thought there were also conjectures about a phase of a gas spin liquid.
Yeah, so that's question, is this a phase, is it a first order transition? That argument continues. I think, yeah, that's related to the other question somebody asked about DQCP. I'm not going to settle that argument. I think the consensus today that there is some kind of almost near confined field theory, which ultimately confines in a generic system. You may have to tune more than one parameter to make it not confined. And in the insulator, yes. And if you allow for charge fluctuation, that's the punchline of the talk today. One thing it can confine to is the D-wave superconductor. So in fact, here, the confinement, the absence of a true DQCP is a good thing. Because if there was a true DQCP, in experiment as you lower the temperature. But as you lower the temperature, you only see confining states. I mean, that's again behind this feature again. This is in the old days. That this state is the same to which would come. And for that, it's important that everything gets confined. Yeah. They're like hedgehogs with the staggering. The spins are pointing radially outwards. Oh no, so this pure QED theory only applies R is large and positive. It doesn't apply when R is negative. So when R is negative, then the monopoles have essentially infinite energy and they're removed. So that's a little different from the XY model. Huh?
Photons are like fixed.
Yes, yeah, yeah.
Comment like concentration, and whenever there is concentration, we get this valence bond solid. So
Yeah.
what's the connection? I'm not getting that quantum mechanically.
Well, I mean, I think so. The point is, there's a nail state, and when you're frustrated, lots of things can happen. It's spiral states and so on. But we asked the question, what happens? Can you get a spin liquid? Okay. All right. So to get a spin liquid, then there are certain constraints that come from the Lieb-Schultz-Mattis theorem, type theorem. The constraints tell you that cannot be a trivial product state. So what are the possibilities? One, it could be a Z2 spin liquid, where the Z2, and it's like the toric chord phase. That would be allowed in principle. And there are certain models where you get that. Or it could break a symmetry, like in the valence bond solid. That's what comes out of the U1 gauge theory, we claim. Or it could be some kind of possible conformal gapless state. And the last possibility is the most interesting. But I think the most recent evidence from the fuzzy sphere numerics is that it's almost conformal, but not completely. That in fact, it's either this or that, depending on some details. Yeah, it's I think it's amazing how this very simple problem has so much complexity that it's taken so long to sort out. But it's really beautiful. Along the way, things in the triangle is it's all well understood, very simple. This is the most complicated case.
These statements are model dependent. Like if I have the same universality, but make a different lattice model, I could potentially
This is
stabilize some other things.
right. So yeah, there can be many different types of VS phases, sure. But they all have the feature that they break translation symmetry and at least double the unit cell. That's required by various theorems.
But like the gap is spin liquid.
Which one?
with the one you mentioned, that
Yeah,
some CFT.
yeah, that's also allowed. So
In principle, allowed. It's
allowed by the anomaly arguments. We don't know dynamically, but it's allowed.
what to do with a lot of small state.
Yeah, these nobody knows really. Yeah,
It's in the statement that you said from Chong that there's always a trivial monopole, so I'll never get a.
that's for the staggered flux phase. I'm coming to that.
Oh, it's not generically true on the square lattice.
Here there is no trivial monopole.
Ah,
This is what gives you, hope of stabilizing this spin liquid. That was what our paper showed in 1989. There is no trivial monopole. They all come with Berry phases. Okay, I will, for the rest of you who didn't follow that discussion, I'll come to that in a minute. All right, so now let's go ahead with the fermionic partons. So initially what you would do is you just write the spins in terms of fermions, just like I wrote in terms of bosons here. Then you have a constraint, and then you say, okay, do the same thing, find a saddle point, and pick some nice saddle point, and that'll have a U1 gauge theory, and write down your U1 gauge theory. So in fact, a lot of people did that, and they settled on what was just mentioned, the staggered flux phase, and that has a U1 gauge theory about it. But it's now understood, starting with a nice paper by Jason Alessier, that in fact that has these monopoles, in fact, are much more troubling than they were over here. There's a trivial monopole, meaning that even a single monopole is allowed, and that's expected to be by all the numbers of the scaling dimension of the monopole operator to be relevant. So a lot of the work that was done in the 90s on the staggered flux phase, to me, has not much meaning because it's just an unstable phase. So what we know today, there's another phase, which was even discovered even earlier by Affleck and Marston, which is the right thing. So everything I'm saying was already known in bits and pieces in the very early days, but how it all comes together has taken a long time to sort out. Okay, so it turns out that this parameterization has bigger symmetry. With this, you would think that the only symmetry is just U1 gauge invariance, just like it was for the bosons. But for fermions and not for bosons, there is a bigger symmetry. And this illustrated here. So you introduce this 2x2 matrix of the Fermi operators. So this matrix is, of course, redundant, and it has certain constraints, which maybe I should remember what they are. I wrote it down. Yeah, here it is. So this matrix satisfies this identity that F dagger F transpose times sigma y, sigma y. So everything in here is just very simple algebra. You just have to go in and work it out and have some fun and see how these identities, very beautiful identities, work out. Okay, so I introduced this 2x2 matrix, which satisfies this constraint, which you can check. And now I can read matrix F and have fun working it out in this form. It's the trace of F sigma. These sigma z's are annoying, but they're there in my convention. And if you don't put them there, they go in other places. So this is all right. So this is just a rewriting of this on every site. Okay, but now when I rewrite it this way, I see something interesting. I see that when I wrote it this way, it seemed like that all I can allow to do is change the phase of F, and that'll give me the same spin operator. But now I see from this representation that I can multiply F by any 2x2 unitary matrix V. That's a bosonic matrix. This is a fermionic operator. So I multiply F by V on the left. So I multiply F by V on the left. There'll be a V here, and there'll be a V dagger here on the right. And by the trace, I can annihilate them, and S doesn't change. So this operation doesn't change S. So this operation here, which is a much bigger operation, is the analog of this operation here. It was just a phase. There was a U1 gauge symmetry. This has an SU2 gauge symmetry. Okay.
Rotation, rotating pipe into a ball. Like after you have dagger.
Yeah, so this is the other pseudo spin rotation, if you wish, where it's F dagger sigma rather than F sigma F dagger. And this, if you work it out, is exactly what you said. And this constraint, in fact, is completely equivalent to this constraint. This should be 0.
What was on these commutation relation?
To establish this identity, you actually use the anti-commutation of the fermions. It doesn't work for bosons. You can also write everything from the Majorana, and but I don't want to do that because I want to then identify the charge. And but again, many of the papers, in fact, in Chong Wang's paper, is all using Majorana, and it confused me no end. For these lectures, I try to do everything in the complex fermions. It is simpler, believe me. But maybe that's the easiest way to see it. If you write this in terms of Majorana fermions, there's 2 complex fermions, so there's 4 Majorana fermions. So you have 4 Majorana fermions, there's an SO4 rotation. SO4 is SU2 plus SU2. So one of the SU2 is exactly this physical spin SU2, and the other SU2 is the V. So that's why there's a second V. So from the group theoretical way, that's the easiest way to see this to be the case. And in fact, what is spin rotations? This doesn't go up. Oh, okay. No, I'll just go over here. So the spin rotation is Fi going to omega I. This corresponds to spin rotation. This is the physical global spin symmetry. There's also some sigma z's here that I haven't put in. I may as well put in because they were over there. Okay, there's a sigma z here and a sigma z. Okay, so, and that you can see, if you multiply F on the right, then you end up rotating Pauli matrix. And that's exactly what you should do for a global spin rotation. So the vector S gets rotated by, if you multiply F by omega on the right. And if you multiply F by V on the left, it doesn't change S. And furthermore, since matrix multiplication is associative, this gauge rotation and this spin rotation commute with each other. It doesn't matter which way you do it, you get the same answer. And then you can also check that these operations, this operation, that operation, preserve that feature. So that pretty much proves all the claims I've made. All right. Okay, so as I said, there was a paper by Affleck and also another by Eduardo Fradkin, who pointed this SU2 gauge symmetry about. And there were some scattered papers who paid attention to this, but everyone was working on U1. I don't know why. So today I'll tell you, take this gauge symmetry seriously and dope it. And this is what was worked out by my student who's just graduating, Wayne Christos. And I'll show some of the nice things you obtain as a result. Yeah.
And logic of these things. If I have some partial theory,
Yeah.
I look at some things as global symmetries. How do I tell, which ones I should promote to gauge symmetries and which ones I shouldn't?
Okay, let me phrase it a little differently. What I would say is this particular parton representation has an SU2 gauge symmetry, period. That is the largest symmetry on each side, which is dictated by this parton representation. Here, the gauge symmetry is e to the I phi, U1. Then I'm going to take a mean field ansatz partons. Now, that mean field ansatz may have a smaller symmetry, okay? And then that smaller symmetry, unbroken symmetry in the mean field ansatz, will determine which spin liquid you're talking about. Okay,
Both these symmetries here, the left and the right multiplication, are global symmetries of that theory.
they are absolutely. So now what do you do? So why do people work the U1 spin liquid? So the way I would say it today is that what happened is they take a mean field ansatz, and that mean field ansatz is in a Higgs phase. It's in a Higgs phase where the SU2 gauge has been broken down to U1. Okay, so working with the most biggest gauge symmetry is always, most safest, because you can always break it if you want, as you wish, later on. Okay, so people chose to focus on the U1 because it's simpler mostly. It looks simpler anyway when you start out. Yeah, but this mean field ansatz is the correct one. Which Higgs phase are you in? I don't know. That's a guess. You have to do numerics to figure that out.
Right now, there's no gauge, right? Right now, it's all global.
No, it's not global. It's gauge. There's an I here. This can be different. V can be different on different sites.
Just internal.
Omega has to be the same on. Sorry. Thank you. There's no I here. There is an I here. Omega is global. V is local. Okay. Yeah. I can't hear you. Yeah. That's not allowed. It turns out it doesn't work. Yeah, I've forgotten why, but if you do the U, right. This is where the Majorana becomes helpful. If you take the U1, if you make this U2, that U1 is actually part of this. It's part of global spin rotation. From the Majorana, the total spin SO4. SO4 is SU2 cross SU2. It's not SU2 cross U2. So there is no extra U1. That extra U1 that you think you have is actually part of this. Okay, so just SU2 gauge and SU2 global is the largest symmetry of this Barton representation. So now the question becomes, let's find a saddle point, which keeps the SU2 actually totally unbroken. So that's not the one people study, but it turns out to be a very, very simple saddle point. It's a saddle point which is written here. The basic feature is your pi-flux per plaquette. You go around any plaquette, you pick up a -1. That's all. But I've written in a peculiar way. I put an I in front. In fact, you need the I to see the SU2 gauge symmetry in a clear way. And the reason I put the I there is because you can also rewrite this way. I mean, you can just work it out. This is equal to this. So that's my mean field ansatz. So I have skipped the step. I've skipped the step. I do some Hartree-Fock theory, and I find spin dense things. In the end, everything is done by just thinking about gauge symmetries and global symmetries carefully. That's all I'm going to use. So here I just write down some mean field ansatz for the spin-ons, which I choose to have an I in front. That doesn't change the flux. You can remove the I by gauge transformation. It's unphysical. There's flux pi around every plaquette. But the reason I want to put the I is that I can rewrite this way. And in this form, it's totally obvious that I have an SU2 gauge symmetry, because if I multiply by a uniform V, then this doesn't change. Okay. Now, so why do I have an I? Well, again, this is one of those annoying things. If you just take this representation, you can check this identity. This is just a negative of that. So since you want the hopping to have opposite signs when you're going this way as opposed to the other way, the simplest way to do that is a pure imaginary. These are all gauge choices in which the SU2 gauge fluctuations are much simpler. So now, once I have this, what is the SU2 gauge theory? Then I can write down the Hamiltonian for HSU2. Well, it's very simple. I just take that, IJ over 2. And I just F dagger I Uij Fj minus F dagger J Uji Fi. And then the analog of that last Maxwell term, you can put something like kappa trace U around a plaquette. This is some over all squares. Okay. So what am I doing here? So this Uij is precisely the analog of this exponential Aij. Here, I'm not taking the continuum limit yet. I will take the continuum limit in a minute. I've forgotten about all the amplitude fluctuations and so on that are not constrained by gauge invariance. So this is my theory now. This is a theory I can give to a lattice gauge theorist and say, I have fermions, which have this very peculiar hopping structure with pi-flux. And then I have an SU2 gauge field. So Uij also has U dagger U equals 1. And also determinant U equals 1 is also needed. I should have said that here also for V. Okay, so this is then my theory for the fluctuations about the pi-flux phase. So this is the very simplest ansatz of fermions moving on the square lattice with pi-flux. And then the full theory of fluctuations about it is this SU2 gauge theory. Yeah. Eij is fixed. It's just a number. That just gives you the pi-flux, and I forgot the Eij, sorry. Eij is just fixed. It's equal to this. That's just a gauge choice. U is a fluctuating 2x2 matrix. So you have a theory where you got fermions on every site, and you've got 2x2 matrices on every link. And this, now you can, of course, see that under gauge transformation, it's an SU2 gauge theory. The gauge transformation Uij goes as, let's see, F has multiplied on the left. So this should be Vj dagger here and Vi. So somebody, doing a theory of quarks, what would be different for them? First of all, this would be a 3x3 matrix, SU3 matrix. They'll have some fermions hopping on the square lattice, on the cubic lattice, but they wouldn't have this flux. They wouldn't have this flux. So there are some other different ways of, here, the flux is very physical. It's the state that comes out in the mean field theory. Yeah.
Is the Eij background from some open inside F? Not here. There's a capital S in the middle border.
Oh, again, I forgot. Thank you. Whether what, sorry? No, it's the fluctuations. So H mean field is kind of like the analog of this Hamiltonian here. So the analog of this mean field is just this or this, they're equal. And the fluctuations, there I went directly to the limit. Here I will go to the continuum in a minute. So this is the fluctuation. So of course, this is a guess. It's not, if I did a very careful Hubbard-Stranovic transformation, large and expansion, I'll get a huge mass. But here, I'm just following the idea that all what you got to do is you find a nice ansatz that you think is a good one for the saddle point of it. And then using gauge invariance and symmetries, you add a gauge field and make everything gauge invariant and study that theory. That's a pretty good strategy as far as we can tell. Yeah.
So how did you?
It's kind of a Landau theory of gauge theories, if you wish. Yeah.
So how did you go from H mean field to HSU2?
I just said, okay, so we agree that if somebody did a lot of numerical work, they found this saddle point. In fact, if you do the saddle point, honestly, it's not lowest energy. That shouldn't bother you because this is approximate, but it's a saddle point. Somebody found a saddle point. And then now this saddle point is not gauge invariant because it's invariant under this only if V is a constant. It's spin rotation invariant, so it's obvious when you look at it that it's spin rotation invariant because there's a trace over alpha. But it's definitely invariant under this. But it's not invariant under this because I have F here and Fi here and Fj there. So this breaks. I mean, this doesn't have gauge invariance. So the simplest way you restore gauge invariance, you just put a Aharonov-Bohm plug. This is exactly like the parallel substitution. You have some hopping, and you want to couple in a gauge field. You say, well, let's see that I get I exponential I a dot dr from I to j times Cj. So that's the parallel substitution. So this is just exactly this. It's the parallel substitutions I have to make the theory truly gauge invariant.
Okay.
Yeah, that's all it is.
That makes sense for the second term.
Oh, this so now I want to write down some term consistent with gauge invariance. So just like for electromagnetism, we know the only way to do it is by the d mu nu minus d mu a mu. For a theory, the only way to do it is go around it like this way, and you take the product of the four u's. When you take the product of the four u's and trace it, then you can see it's also invariant under this. So it's the simplest term involving only u's. Now, if you take the continuum limit of this, then you get the non-abelian gauge field. F mu nu is d mu a nu minus d nu a mu minus commutator of a mu minus a nu. All of that will just come out of this. So this is the discrete version of the Yang-Mills action. It's a lot simpler than the continuum version. We don't, yeah. Yeah.
Invariant?
Yeah.
It seems to be U2 invariant.
No, it's not. Yeah, I just answered that question. If you try to work it out, it won't work. You just have to sit down and work it out. It's not U2, it's SU2. Yeah, those sigma z's come in and change things a little bit. I don't remember, but I showed it doesn't work. There can't be U2. There is that U1 is sort of like a rotation about the sigma z axis. It's like a spin rotation. You will change SZ to minus SZ, but SX will remain the same. That's what I think that U1 is. Yeah. Yeah, you can write it down that way if you wish. I mean, it's triangular lattice. I don't know if there's an SU2 ansatz that's possible. You really do need a bipartite lattice for this to work. You have to make every bond purely imaginary. At least that's one simple way to do it. Yeah. Yeah, so it turns out a triangle lattice, there is no simple SU2 ansatz. I guess there could be in principle. But the U1 there works actually. And there's numerical evidence there and so on. But that's a whole different story. Okay, great. All right, so the next step, which I thought I would go through all the steps, but again, they're in the notes, is to, just like we went from here to there. So let's take the continuum limit of this beast. So this beast, this is some SU2 gauge theory, has exact SU2 gauge invariance. It's got some fermions coupled to the gauge field. It's just like quantum chromodynamics, essentially, with a few twists. And global spin rotation symmetry, exact global spin symmetry, although that's not evident from the way we wrote it down. It's evident over here, but why don't I just put an SU2 gauge field in here Well, then it has a very complicated coupling in here. No, actually, this form, even spin rotations are invariant. There's a trace here, I forgot. Yeah, it's all fine. Even spin rotations are evident. Just plug this in here, it's fine. And there you go, that trace should be there. Okay, so now we want to take the low energy limit of this. And here the low energy limit in some ways is very simple. It's something you've done for graphene. Essentially, you look at the fermion dispersion spectrum, find where the Fermi level is, and then just take a uniform limit. Here, you have to be a little bit more careful with the gauge field and so on, but anyway. So what do you get? So first of all, if I ignore the gauge field, imagine the gauge fluctuations are weak. You know, the whole theory is predicated on the fact that the gauge fluctuations are not strong. If totally strong, then your mean tidal point means nothing. So you should be able to expand about U close to 1. Now, would still have strong effects. Even small fluctuation of U could have small effect. You know, that's what happens that's confinement in quantum chromodynamics. But let's just start and see what the continuum limit looks like. All right, since I do want to get the charge part, I will skip the details again, but every step is there in the notes. So if you look at the dispersion, so for U equals 1, what is the dispersion of the fermions? So the dispersion, well, you can see the picture here. It's sort of like graphene. There are 2 Dirac nodes. EK has Dirac nodes. 2 valleys at 0, 0. And so in that gauge, it will be double the unit cell in this direction. So it has to be 0 pi. Okay. So what you do is just like you just write f of I is say f1 of r as e to the I, well, let's say fv e to the I kv dot r, sum on the 2 valleys v, and this is k1 is equal to this, and this is k2 is equal to this, and v equals 1, 2. Okay, so the 2 valleys are the points. Let's make this capital K. So these are the 2 Dirac nodes. It's just very similar to graphene, K1 and K2. And then you just write down in each valley some slowly varying fermion field. Okay, and then you take the continuum limit. All right, so here is a bit more complicated than graphene because these are matrices. But in the end, it becomes relativistic. And I will skip the details since I only have an hour left. So where's my glasses? Okay, so what you get, so the low energy limit, it's really extreme. Well, I write it in the maximally simple form, L of F. So this is some continuum field. The 2 raise F bar and gamma mu d mu minus I sigma L A mu L F. Okay. So exactly what is F bar in terms of the others and what the gamma mu are, I refer you to the notes. It's a rather complicated set of, there's, again, as usual, there's valley space, there's sublattice space, and there's spin space, and there's also the matrix structure. You have these 8x8 spaces, and then you just take the usual. It's baby stuff compared to twisted bilayer graphing, which is even more indices, but it's the same idea. But here you have the gauge field, dynamical gauge field, and roughly speaking, basically Uij is exponential of I, the SE2 matrix, sigma L, AL of IJ. So we just write it that way. So there's three fields. So L goes from X, Y, Z. This is X, SE2 gauge field. And you just expand this out, and this is what you get. So it's, what, sorry? Everything is 8 by 8. Yeah. There's a valley index, sublattice index, and spin index. Yeah. So there's three types of matrices, which I call rho, sigma, and tau. I refer you to the notes. I will definitely make a mistake if I try to write it down up here. And I haven't skipped anything again, I promise you. And if you take this, put the same thing in here, you get the usual Yang-Mills term, which I will just write as trace sub curly script F. I don't know, it's something minus d nu a mu squared, something like that. It's the non-abelian version of the Maxwell term. And that comes out a product of U's around a plaquette. All right, so you have this now, here we had a theory which was a U1 gauge field with two complex scalars. And here we have a SU2 gauge field. And it turns out there are two valleys, basically two massless Dirac fermions. So here, at least the way I've written down, this term is not that important. There's no coupling constant. It's a theory with essentially, basically, other than the gauge coupling, which expected to flow to strong coupling anyway, is just unlike this theory that does have this coupling R. Yeah. A similar thing where you have this constraint, and it comes from the. Sorry? Yeah. I didn't write it out, but yeah, its saddle point value is 0, so so I was justified from that. Yeah. Well, there's 3 gamma matrices times gamma y something. Yeah, that's right. These are 2 components. That's correct. That the Dirac space is 2 component, but there's other spaces which are valley and so it's unitary. It's a unit matrix in valley and sublattice space. Actually, it isn't. It's complicated. Okay, if you think in terms more abstract in the algebra of matrices, here in addition to the the valley is like a flavor index. So. Yeah, the microscopic lattice flavor index is slightly different from the continuum flavor index and so on. But once you go to the continuum limit, you can just think of it as 2 by 2 matrices. Sorry. No, but these are very important points. In fact, getting all these gamma matrices right is at the heart of everything, and also the understanding the broken symmetry. No, okay. So what I call the sublattice space, which is 2 by 2, is the gamma matrix space. Okay. That the gamma matrices acts on sublattices, even on graphene. But the sublattice definition is different on one value than the other. Yeah, okay. So that leads to some stuff, which is all in here. All right. So now, now comes the, I guess this was the remarkable fact. So for this particular field theory, now you have this field theory. So it looks, very much like QCD in one higher dimension. So massless QCD would be 3 quark flavors and SU3 gauge group. Here it's 2 quark flavors and SU2 gauge group in the continuum limit. And so what are the possible phases of such a theory? So what we know for chromodynamics in 3+1 dimension, it is always confining, at least for 3 quark flavors. Okay. And when it confines, you break Connell symmetry, you break a certain symmetry. Okay. So similarly here, you can ask, what happens with this theory confines? Which symmetry will I break? All right. So there's some natural way to see that, is that if you take this theory and ask for what is its global symmetry. Okay. Now the global symmetry here turns out to be SO5. And exactly why it's SO5 is something that I've derived in the notes. Sorry. It's not complicated. You just have fun with Dirac matrices, with Pauli matrices, and you can show it. But let me give you an abstract way of seeing that. Okay, as always, if you want to really see the full symmetry of any theory, you write everything in terms of real fermions. Okay, so here you have 2 Dirac fermions, which are complex. So when you write it in terms of real fermions or Majorana fermion, they become 4 Majorana fermions. And then there is, what is it? Then there's also the spin index, this gauge index. So that's really 8 relativistic Majorana fermions. So that the free action for that has an SO8 symmetry. However, SO3 of that is gauge. You can't break the gauge symmetry when you confine. But in a confining phase, the gauge symmetry is preserved. So you have SO8, you pull out SO3, and you're left with SO5. So basically the net result is that when this theory confine, there is some vector, which I'll call gamma sub t, where t goes from 1 through 5, which is something like trace of F bar, some matrix, TF. So what's shown in the notes is that there's some matrix like this, which transforms as a vector under the SO5 symmetry of this Lagrange. Yeah, okay. And don't be scared, it's all there. It's all a matter of just commuting Pauli matrices and seeing that that's the case. I don't use the Majorana representation at all. Once you dive into Majorana, I get completely lost, but this works, okay. Anyway, so you have this 5-component autoparameter. And so our knowledge of QCD now tells us that if this theory is confining, then it's going to break a certain symmetry. And we know it had to, again, the Lipschutz-Mattis theorem tells us, if you have some gauge symmetry, you got a spin liquid, and you're getting rid of the gauge, your fractionalization, then you better break a symmetry. Okay, so what is this vector in physical terms? This is a physical gauge invariant object, which you can now figure out what is it. Again, I refer to the notes. What are these? What is that 5-component vector? It's 3 components X and 2 components X. It's exactly the Néel VBS autoparameter. So this is telling us that this theory has 2 possible fates. One, that it just confines. And if it confines, then depending on some details of higher order terms, it will either fall on one side with the Néel order, other side with the VBS order.
There's some anisotropy.
Correct, yes. Those are the Fermi terms, which I haven't written down, which are allowed. Or it could be, if you take QCD in 3+1 dimensions, I forget what the number is. The number of quark flavors is greater than 11 or something, or 11/3, something like that. Then, in fact, it's a conformal field theory. It's a fixed point, which is scale invariant, which has no quark particle. It's a strongly coupled conformal field theory. So if that's conformal, then it will probably mean that this is a whole critical phase here. So it's really what I'm mostly interested in, that the nearly conformal thing. And this fact that these autoparameters are exactly the same in the confining phase is basically the content of the duality proposal by Chong Wang et al. All right. Okay, so after a lot of work, a lot of very hard work, in 2018, we finally found a picture that we already knew 20 years earlier, studying the bosonic phenomenon. Got the same picture. So it's kind of amazing that even this very simple square lattice antiferromagnet has this spin liquid state that is so complicated. Is that two different descriptions? One is this QCD theory, another is that theory. They are supposedly the same, but it's strong. They're both strongly coupled, and we have really no way of, and certainly numerically, I mean, with any kind of numerical accuracy, computing anything. You have to do some serious numerics on the computer to really understand what's going on. Yeah. How does it go confining? Well, the same way quarks confine in 3+1 dimension, the non-abelian gauge force has a strong attraction between quarks, and they form gauge-neutral composites. In this case, they form mesons. You can think of this as a meson. The Néel order parameter is a meson. And there's 5 different mesons. It's very much like chiral symmetry breaking also has 8 mesons or something. So there's a soft symmetry breaking because the quarks are not exactly massless. There's some bare quark mass that here there is no bare quark mass. Here the quarks are exactly massless. Yeah.
Somehow.
Yeah.
very
Yes.
A step back.
Yeah.
Maybe not very surprising in that, the phases that you're getting
Yeah.
are confining phases.
Yes.
So in both of them, bosons here are confined
Yeah.
and here fermions are confined. Then the only thing you're getting is the physical order parameters that are
Yeah.
spin.
Right. Yeah. But so what people who do numerics, what they find is that, system sizes as big as, I don't know, 50 or 100, it seems like the thing is just critical. The confinement seems to kick in at the so for our purposes and the rest of this lecture, we could just assume, let's just assume it's critical and see what's going to happen, because we're only going to apply this at finite temperature anyway. So that's going to act a natural cutoff wherever you can apply it. But I mean, it's only the SU2 gauge theory that does this. If you take these, so there was a paper by Senthil, Fisher, and Hermanli who tried to do exactly this for the staggered flux space. Got a huge mess, all kinds of 20 different order parameters. But when you do with SU2, you get exactly that.
Getting that sort of.
Yes, yeah.
Sorry, I don't think I understand the anisotropies. So there's
Which anisotropies? Oh, in SO5 space?
there's a global exophi everywhere.
That's correct. So this theory has a global SO5 symmetry, but I can add terms, some F bar. There are various terms over here which will break the symmetry. Those are allowed. And they're in fact, the terms are basically, the term I can add is basically a gamma. I can add a term like gamma 1 squared plus gamma 2 squared plus gamma 3 squared minus gamma 4 squared minus gamma 5 squared. So that turns out to be allowed by the symmetry of the square lattice. I mean, you can already see over here, there are two possible, this has a Z4 symmetry of rotation. The symmetry is only Z4, but even the VBS comes out as U1 in the low energy limit.
But there's no SO5 anywhere in that phase diagram, right? If, for example, if there's an
So people have taken the J model and studied this critical point and numerically found an SO5 symmetry.
well,
There's a work by Sandwick on that.
but even if there is conformal symmetry, the SO5 is emergent, right? There's no microscopic SO5.
Oh, absolutely. Yes, yeah. So in the end, if there is no conformal symmetry, there is no emergent SO5. If and only if there was a conformal fixed point, would there be an exact emergent?
That theory, criticality is fixed to be at the point where that SO5.
Well, it could flow to zero. We don't know. Under RG, it could flow to zero. That would be the conjecture, that it flows to zero. It doesn't seem to, but that was a hope for a while. Yeah.
The spin-ons are gap.
Oh, no, I'm sorry. No, that's not a correct statement. That last term there, gamma squared, is the same as R. So you'd have to tune that, yes. But it could also be relevant, yeah. Yes, yeah, but once you can, yeah.
Your comment about the staggered flux being, surely if that's embedded in this theory, I should be able to see that as something over here.
So the staggered flux is a U1 and it has to have all kinds of monopoles. So it has a relevant monopole. And the conjecture is when the monopole goes relevant, it actually flows to this SU2 theory. So the nice thing about SU2 is it has no monopoles. So you can, all the nonsense about monopoles you can forget. And all the complexities of the symmetries just comes into part that I skipped, which is in the notes, just dealing with these 8x8 matrices carefully. Which, as I have said already, is baby stuff compared to what you do in TBG.
So explain the comment again about the critical fade.
Yeah.
In what scenarios one gets a critical fade?
So, the scenario would be where that term flows to zero. Then it would be a phase. If it has to be tuned to a point, then it's a critical point. And if that term it flows off to strong coupling and confines, then it's a weak first order transition. Yeah.
So what one can match up between this and that are the phases.
But the paper of Champagne et al. Has very sophisticated arguments based upon anomalies in 3-1 dimensions and SO5. I don't understand it, but that content of is what I've just said.
Well, I guess I'm just asking you to repeat.
Yeah, no, I think content of their very fancy SPT arguments, which are very elegant, but for pedestrians like me, the content is simply that the confining phases of this theory are the same as the confining phases of this theory. It's no more, no less than that, I think. Someone might correct me. Yeah, Senthil was here, he might be yelling at me now, I don't know.
EPS state you got here came from monopole carrying momentum in some condenser.
Yeah.
While over here is just the SO5 spontaneous symmetry right here.
Yeah, so
Watch the symmetry that he put with sublattice.
So there's there's all these papers on gross-Nouveau lattice model by Igor Orbert, where the only difference, doesn't have a gauge field. And he has this Dirac Lagrangian with all kinds of,
Dirac fermions contain sublattice.
yeah, so in his theory, there's a global SO8 symmetry and you can break it in different ways, depending on higher order coupling. So this would apply to graphene in strong coupling somewhere. The only difference from what's done for TPG or bilayer graphene is that here, the SO8 symmetry, you gauge SO3 part of it, that's all. And then the lattice indices are somewhat different because you have this pi-flux and so on. It's on the square, not the honeycomb lattice. Yeah, so Igor was all on the honeycomb. Yeah. Yeah.
Mentioned that there are some other sample points would be.
Yeah.
They all also go to this picture if you include some pictures?
No, well, we don't know. I mean, we believe so then we have to rely on numerics. So now there's been all these beautiful numerics on the J1, J2 model, the JQ model, and then also on the fuzzy sphere on yet another representation using a Westermino-Witten model. And they all give basically the same answer, that is either nil or VBS, or there's a very wide region where it's just essentially critical.
And if I try to play this game with the other sample points, like looking at the.
Well, we don't know what the saddle points mean because we don't know where they're realized in any real Hamiltonian. As far as we can tell for this, the popular one is the staggered flux. It's so strongly unstable to monopoles that I would expect there is no lattice model in which even that's a good approximation. Yeah. Yes, yeah.
Dispersion, shouldn't they be Dirac constant 5 by 0
Well, but I doubled the unit cell because of the flux. So really the unit cell is 2 by 1. And so So pi 0 is not allowed because it's the same as 0, 0. So that's different from honeycomb. Okay, so then finally to the punchline. All right, so now what I want to do, so like I said at the beginning of my lecture, why bother with all this? You know, well, the reason we want to bother with this approach has a very nice connection to superconductivity, which was already recognized in a more pedestrian way in the early days. And in fact, the superconductivity is precisely dx squared minus y squared. And it comes out of here, and you can view this as the kind of the spin liquid analog of the Fermi liquid calculation, but it also gives you x squared minus y squared, the two ends of the cuprate phase diagram. All right, so let me show you that. So what I have to do, so in fact, the calculation, this is in the paper with Main Christos and others, a couple of years back. We can again just think in terms of symmetries. All of this was just, all I needed to do all of this was just know the pi-flux, and there's an SU2 gauge field. That's all really I need. Everything else just follows from that. And so here, let's assume you have such a phase. Now we're going to put in some charge fluctuations. So either you're doping the system, but more simply, you're just reducing the value of U. So you're taking some TUJ model, maybe other interactions, where you're in this pi-flux phase over some intermediate length scale. And then you're asking, is there any other route to confinement? So two routes I've already seen, either nail or VBS, but is there some other route? And I want a route that involves charge fluctuations, so I have to introduce a parton that carries charge. And then secondly, I have to have the electron operator around, because that's a physical operator in any theory that carries charge. So I have to have the electron operator. So I'll define C is C up, C dagger down. This is the physical electron operator, minus C down, C dagger up. And I'm going to introduce a boson, which I'm going to write so on every side, it'll be B1, B2. It's also have this SU2 form, minus B2 star, B1 star. These are bosons. And I'm going to require that the physical electron operator, which should be SU2 gauge invariant, is going to be C, will have the same properties. Need not be any quality, but in the terms of symmetry, these operators should transform the same way. Would be, so this is script B, let's say, B dagger F. Okay. So I'm going to introduce the charge E boson. We'll see what the charge is in a minute, such that when I fuse these operators and bring these operators close to each other, I get an operator with the quantum numbers of the electron. All right.
1, 2 sublabs.
No, 1, 2 is the SU2 gauge index. And now, since the fermions have a SU2 transformation, the boson must also, because C is invariant under SU2. So I must have the fact that script B under the gauge transformation will be also V times script B. Because if this is true, then you can check that C will go to C. And then under the omega, the omega, remember, acted on the right. So omega rotates electrons because it's spin, and rotates F, acts on the right, so it does do nothing here. And then similarly, you can see that these bosons B1 and B2 have charge E. So basically, the summary is that this B is some boson. It's spinless because it doesn't transform under spin rotation. It's the SU2 gauge fundamental. And then it has charge E. So these are all the things I know about this boson. Finally, I have an operator that will allow me to create an electron as a local physical operator in my Hilbert space. Okay. What else do I know about it? Well, there's one very important thing I need to know about it. And that is this boson must also move in pi-flux. And that has to do with the what are called the projective symmetries of the lattice. So the electrons are gauge invariant, so this flux is fake. Any physical electron cannot see the flux. So if F is seeing a flux, B better also see the flux, because then their composite will give you a flux of 2 pi, which is nothing. So this flux that was acting on the boson, on the fermion, must also act on the boson. All right, so that's really all you need to know. You need to know these properties and that the fact there's a flux, and then you make sure you satisfy square lattice symmetries, either projectively or not, and write down some action for the B. So very general argument. So you do that, and what do you get? So again, this is I keep saying it, compared to what people do for bilayer graphene, this is very, very simple. So you get some energy functional for B. So I'm just going to do pure mean field theory. So here the idea is that I have this spin liquid, which is nearly critical, almost confining. And instead of allowing it to confine by forming a Néel state or VBS state, I'm going to Higgs the gauge symmetry. B is going to condense, and it's going to give me some phase. And I'm going to ask, what is the phase that I get that way when I condense this minimal boson that has to be there in the theory once I have charge fluctuations? And I use symmetries to write down some general energy functional for B. So you get something like R, the different R, beta I get B. Those are the usual Landau expansion. But I'll work still on the lattice because the flux, but you can later on take a continuum limit. Then it'll also have imaginary hopping, exactly the same as the fermions. Or minus beta. And then there's a whole bunch of quartic terms, which I won't write out, but you can find in the notes. Okay, so this is my theory for some boson, which carries the SU2 gauge charge, so it must couple to the SU2 gauge field. But I'm going to take a very simplistic point of view. This boson, this is like the Higgs boson of, in fact, the parallel to theory of weak interaction is kind of striking. There's a Higgs metal. There's an electromagnetic U1, which commutes and is not broken. Here there's an electromagnetic U1, although it's global. Anyway, and what do you do when you do the theory of weak interaction? You just condense the Higgs boson. It gives all the fermions a mass. Now, in that case, the condensing the Higgs boson doesn't break any symmetry. It turns out, for the theory of weak interaction, the Higgs symmetric and the Higgs broken phase are the same symmetry. Here, because of the pi-flux, you're forced to break a symmetry. You have to break a symmetry. Just when you work out all the symmetries carefully. I know I'm rushing through. Anyway, so basically you do mean field theory on this. You do a systematic analysis of what symmetries will be broken. In the very simple theory with only nearest neighbor couplings, you get 3 phases. So you just look at phases with B not equal to 0 and all their properties. And what you find, this is the Landau theory on the lattice. You do have to put it on the lattice because of the pi-flux. You can take a continuum limit. You get 3 phases. One is a D-wave superconductor. And the way you see it, you get some condensate of B. Now, B itself is not a physical thing. It carries, it's a transform under gauge. You can change B to some other B by this gauge transformation. So you have to look at gauge invariant combination. You take your condensate and look at all possible gauge invariant combinations. And from the symmetry of the gauge invariant bilinears, you can deduce what's been broken and how it's broken. So one of them is a D-wave superconductor. And the other of them, in the simplest theory, are stripes. Stripes, period 2 stripes. And in more complicated theory, you can make them 4. Period 2 stripes. And the third one, not so interesting because never seen experiment, is staggered currents, or sometimes called the D-density wave, which various people have also talked about, but that doesn't seem to be experimentally relevant. Anyway, so you get a D-wave superconductor. So that's very exciting. And you also get stripes, which you can adjust to make the right period. So it seems like you're getting exactly the phases you see. And by playing around with this potential, you can fit the physical phase diagram. And this, and it's not S-wave. And furthermore, it's not just a D-wave superconductor, it has nodal quasi-particle. Okay. All right, so seems like we should declare victory. But there's a problem. So remember that the fermions here are relativistic. So that means that we have the Dirac nodal point. It's a perfect cone. It's not elliptical. So those fermions, the spin-ons, become the nodal quasi-particles of the D-wave superconductor. And that's actually not what happens in the real world. And the reason we know that is that if you look at the actual nodal quasi-particles, they're not circular cones. They're very squashed cones in their dispersion. So the dispersion, near the nodes is something like square root of what we call VF squared times K1 squared plus VF squared, V delta squared, is squared. So VF is the direction normal to the Fermi surface. V delta is the direction parallel to the Fermi surface. And in this theory, VF equals V delta. But in experiment, what we know is that VF was much, much greater by a factor of 10 than V delta. And this was one of the reasons this theory was kind of abandoned. Because it doesn't seem to make sense that the spin-ons are what become the Oglyubov quasi-particle D-wave superconductor. That's not supported by the experiments.
There's nothing in that theory that breaks the rotation.
No.
Rotation symmetry.
But there's a certain, no, they won't. That's right. I mean, because there is no Fermi surface to begin with. It's just from square lattice symmetry for the pi-flux phase, the two velocities have to be equal. So
value in the continuum.
Yeah, I think you can, I mean, it's an exact statement about the Dirac node.
It's a long way.
The node is a stable node. You can't remove it, and the two velocities. Even in graphene, that's the case. It is a perfect cone. That's true for any graphene, but it's not true for the Oglyubov quasi-particle. They're very squashed. Okay, so that I will fix on Thursday. Okay.
So from a BCS perspective, we delta is given roughly by delta over there, right? The maximal gap. So should I think of your statement about symmetry that delta should be EF to get?
Yeah. So that's right, and it's not in the real world. It's very far from that. So the spin liquid theory would predict that the gap should be of the same order as the Fermi energy. That's what the spin liquid theory is saying, at least this version of it. Okay. And that's clearly not correct. So that's another way of saying the problem with the spin liquid theory. Yeah. People try to, in fact, I talked to Patrick, who worked a lot on these ideas from the very early days. And he said this was the reason they abandoned the SU2 gauge theory, but they had this in the staggered flux phase, they can make the two energies slightly different, but not much. I mean, by a factor of, 2 at most. Experimentally, the factor is 15. So that was the reason the MIT group worked on the staggered flux phase for a while, because they were trying to fix this problem. but it has other problems. Much more serious problems, yes.
Should I think of could I think of a pairing glue for this D-wave superconductor? What is the thing?
Yeah, no, I think what this is a practical realization of the physical idea of Anderson, that you had a spin liquid, which already has pairing. And that pairing is built into all of these SU2 gauge structure of this, I write it in a form that there's no pairing because of by an SU2 gauge transformation, but you can also, because F and F dagger can rotate with each other and so on. So there is some kind of, there's already built-in pairing correlations in the spin liquid, and all you're doing by condensing this boson is making those pairs mobile. This is the practical realization of that idea.
Could we define what the question was about the cuprates?
What the question was?
If I wanted to get D-wave superconductivity and D-density wave and stuff, I could just do Hartree Fock BCS on cuprate.
Well, then you wouldn't get the pseudo gap. That is the question. Yeah, the question.
Yeah,
So that I said this yesterday, that I have no problems with the old-fashioned theory of Scalapino et al., provided I can see a large Fermi surface, because the theory rests on having a Fermi surface which has a Luttinger volume. I mean, you can't just put fluctuation and change the volume. The Luttinger volume is a very robust thing. The entire theory of weak coupling superconductivity, if you say, well, let's just forget about, not worry too much, don't worry, be happy, take the weak coupling, put it to strong coupling. I mean, I do that all the time, fine. But that would, for me to be satisfied with that, I would want to see the large Fermi surface above TC. That's the issue. It's very much linked to this pi-flux. I mean, I wish I had a better answer. You don't get answers. There's definitely something about the square lattice spin liquid that likes D-wave. And it's a very different argument from the Fermi surface argument I gave last time, which looks at all these hot spots and all of that. So that suggests, there's some continuity between them. But this one doesn't seem very continuous. This is a problem here. The key will be a property of the pseudo gap. How is the Luttinger theorem violated? Which is what I'll turn to on Thursday. And once you solve that problem, all of these things get solved. Yeah.
So, do you mind saying again why in this theory V delta turns out to give you an actual gap of E Fermi? I would have thought that you could.
There is no E Fermi here anyway, right? Yeah, J, it's J. They're equal, basically. It would be E Fermi in the other theory. Yeah. Well, I mean, if you just took a PCS theory of a D-wave superconductor, for us to get VF equals V delta, you need the gap to be a part of the Fermi energy. Yeah.
So if I take that fermionic theory,
I mean, one more thing I should say, that this, on the other hand, this is a quantitative problem. It's not a qualitative problem. In all other respects, in terms of symmetry and all the other properties, this state is basically the same as a VBS state. So it's not as serious a problem as you might, but it is still a problem.
But the problem isn't wanting to get V delta big, it's wanting to get VF small. You want to get VF such that the typical age.
No, you want VF large. You want to get VF much larger than J, something. V delta is about a J or something. Yeah. Well, okay. I don't know. The gap is, I don't know, 13 maybe. And yeah, the gap is about J over 4 or something like that.
so if I take that fermionic theory, with you wrote that gamma squared, a couple of them.
Yeah. Yeah, exactly. That's exactly. You get a medal for that. Yes, correct. That's how you get it. Yeah.
I try to focus on the new VB application. Is that the case that in the critical point, the Dirac forming is gapless?
Sorry, there is no Dirac fermion here. So in this theory, there's a gapless boson. Let's go to the critical. There's a gapless boson and a U1 gauge field. Yeah, so what is precisely the relation between this boson and that fermion is highly non-trivial. So this is a strongly coupled conformal field theory. In fact, formally speaking, it has no particles. It has only operators and scaling dimensions. It's strongly coupled. And so how do you write down the Z alpha operator in terms of the fermions or vice versa? I think Sensil will be the expert on that. You have to combine this Z alpha with a monopole in some strange way, and then you'll get that fermion. Yeah, that's what's in the paper by Chong et al.
We need the realization of this or
This is I'm not computing any numbers. I'm just doing mean field theory so far. Yeah, so and I'll continue to do that. But yeah, so this is what I'm presenting is some general Landau theory argument in the spirit of Landau theory for gauge theories, and seeing how far that can get me. But to actually compute the Landau coefficients is a hard task. But hopefully, once we find the right Landau theory which is working correctly, then we can now do the next task of relating that to microscopic couplings.
So to go from the theory with fermion to the
Yeah. Yeah. Yeah, I mean, here, in fact, they're also there. I'm just trying to look at, the full theory, I would say, is this term. It's this term. And there's also like a Yukawa coupling I can add. It's something like, E dagger, some lambda. So I have this theory and this term in the continuum limit, or really on the lattice. And then I have this term. So that's my theory. That is the full theory. That will at least describe the low doping region. Next time I'll present a theory that even has a high doping region. That's more complicated, but this will get everything in principle. So I'm just saying, okay, so this theory is a gauge theory. And I have a strong suspicion the gauge theory is going to confine. So how can I confine it? One, I can ignore B and I can get a nail of ABS. Or I can condense B and get, what do I get? Now, I do have to worry about the electron charge density and so on, and how that leads to Fermi surfaces, but I've ignored that. That's the topic of next lecture. This is, no. So this, at the moment, I'm imagining some model where the half filling had a spin liquid, and then it just went into a superconductor. I've gone directly from the nail state. If you wish, yeah.
want to get somehow it's excitation.
Yeah, so I haven't really worried about the fact that there is a Luttinger constraint on the Fermi surfaces of these Cs. I haven't put that in yet. I will do that next time.
I will take the last question.
Sure.
It's related to what he was asking and so
Yeah.
I mean, at this point, when you have a spin liquid, you
Yeah.
get the D-wave superconductor. But
Correct.
what is the stiffness of that superconductor? Do you get a finite TC or zero TC? Because I mean,
No, it's a finite TC. I think it's fine.
the stiffness is coming from
From here, it doesn't matter. I mean, they're both particle and whole fluctuate. I mean, you can, this is very general. The fact whether there's dope charges or not has to do with the time derivative term of the, sort of like the Bose-Hubbard model, right? You could get half filling, or, you have this mod. You have the mod lobe here. Whether you're at the mod lobe or away from the mod lobe depends on whether you have first order time derivative or not, which I just ignored in the mean field level. Okay. So there is this definitely gives a stiffness. It gives a stiffness to all these orders. Yeah, yeah. But I just wrote it down. I don't know what W is. If you're trying to really start from a TJ model and try to get that, yeah, then you will get a delta in front of it and so on. And all the secret, if you try to do macroscopically from a TJ model, you will get, yeah, maybe you run into issues here. This W becomes small.